So this is Jeff Hamrick at Rhodes College, and I'm going to spend a few minutes running through a randomization procedure that we've learned in class recently. This randomization procedure is appropriate when we have a dichotomous independent variable and a quantitative dependent variable. So let's recall the example we've been working with in class. We have two groups of students. One group of students was exposed to an open book examination policy. The other group of students was exposed to a closed book examination policy. And using a summary table here, we execute a relatively superficial analysis of the set of data. We see that students exposed to the open book policy do slightly better. They get 191.357 points, as opposed to the closed book students who on average get 190.619 points on the exam. Now, we should be pretty suspicious about whether or not the difference between those two means is large enough to really conclude that students do better when they have an open book policy. There's probably a fair amount of intrinsic variation to the data that would sort of make that apparent difference much less remarkable. But we'll use a randomization procedure to make that idea clear in just a second. So what's the idea behind this randomization procedure? We're going to assume that we're going to create an artificial universe in which the distinction between open book students and closed book students doesn't matter, because that's what we're going to test our actual data against, this particular universe, this particular set of simulations that we're going to create. So to create that universe in which we repeatedly run an experiment of collecting a pseudo group of 263 students and measure their mean test score, I'm going to sample repeatedly without replacement from the original set of data, ignoring the distinction between the students exposed to the open book policy and the closed book policy. So recall that we do this in Fathom by sampling cases. Okay, we don't want to sample 10 cases now. We want to sample 263 because I'm going to sort of synthetically create groups of size 263 to say, okay, what is a group of size 263? What does its mean look like if the distinction between open book and closed book doesn't matter? So that's why I've changed this 10 to 263. I'm going to shut the animation off, make sure I sample without replacement. And let's take a look at one of our samples right here. We see that we do indeed have 263 students sampled without replacement from the original set of data, and now I have to define a measure. The measure of interest in this case is the mean. So over each sample taken without replacement, I'm going to impose a measure called the mean. So I'm going to say mean test score, and this is an easy formula. I'm going to take the mean of the final exam score. Remember, I'm ignoring the book status, whether it's open or closed, I don't care, because I'm simulating a universe. I'm creating an artificial world in which there's no meaningful distinction between open book and closed book policies. So I'm going to ignore that attribute for right now. And I see in this particular sample taken without replacement, I have a value of 191.833. So I'm going to close that out. That's one measure. I want to collect many measures. Okay. 1, 2, 3, 4, 5 is the default. I want a number much higher than that, like let's say 1,000, and I want to delete this table so that I can speed up my Fathom workspace. So I'll turn the animation off here, and now let me collect those measures. It's going to take a few minutes, so I'm going to go on ahead while this is running and close out this particular session of the screencast, and in a second screencast we'll finish this analysis. So let your measures continue to collect and click over to the next screencast and we'll finish out our analysis.